Hello, today I'd like to start the course on Calculus 1 and uh, we start of course with introduction of real numbers. Those will be the central objects of interest of the scope of lectures. And Calculus 1 is basically the art of reasoning about the basic calculus concepts that can be viewed in the setting of a calculus of one variable. So calculus 1 is one variable calculus. I think we jump right in, and this is our first definition. Well, I don't know how I would like to enumerate it. Maybe mm, just use enumeration that follows. Just to introduce for any new definition, new number, and for any new theorem. Well, I'm not so sure about that because I have not divided it into chapters. Okay, let's say definition 1 for now, and then I will decide when the first chapter will end. For example, like that. We begin definition 1, real numbers. We define real numbers in quite an abstract way. You should watch my videos on basics of university maths to have a certain level of mastery of concepts that we will involve without mentioning them explicitly anymore. So that background you should either possess or you should watch those videos. Alright, video numbers. I will assume it from now on without mentioning it anymore. Okay, but some things from the year I will of course repeat because I want this introduction to be more or less self-sufficient. Only that um, I would not like to talk about maps again and stuff. That was covered in my series on basics of university math. So if you like those prerequisites, then go there and watch those videos. All right, real numbers are a field with certain additional properties that we'd like to impose on it. But first, let's discuss what is a field. And this definition is rather lengthy, so we'll start by the first thing. And the first thing is just how a field works, and that is operations on real numbers. And operations are just maps. Okay, let's call them in the customary way. But no, let's not do it. Okay, video numbers, uh, let's just do it like that, are a set. Okay, with. And so the definition begins. As I said, first of all, it is a field. What does that involve? Well, Operations on real numbers are the first part of the definition that describes the property of real numbers of being a field. Operations on real numbers. I should probably mention that there are different approaches to creating the number foundation for calculus. That is, for introduction, the basic sets of numbers, the natures, the integers, the rationals, and then the reals, and how I name those sets now. That would correspond more to the down top approach. So we go through the most basic structure that we define axiomatically from the natural numbers to the highest level structure, real numbers, in steps from natures to integers, from integers to rationals, from rationals to reals. That is one way. I will not go this way here, but maybe I will mention something about this way. Probably not, because there are some constructions involved which I'd like to postpone, like equivalence classes. If you'd like an example, uh, I'd like to postpone the corresponding definitions. And I take the top-down approach where we define the real numbers axiomatically. And the object that will enjoy all the properties that we will require from this set to satisfy will indeed determine the totality of the real numbers. Okay, and maybe you should keep in mind from school, even though we'll not see soon how it is connected, you should keep in mind from school that the real numbers are just the float point numbers. That is, any infinite sequence that has some integer part, infinite integer part, having some numbers here. Let's just denote them like, no, let's go like that. A1, 2, A3, and let's use the decimal system. Probably you know that we can write the numbers with different numbers taken as the numbers of whose powers we take to think of those powers as positions. But if you don't know about positional systems, don't care about that. Those are just numbers from 0 to 9. That's all you need to know for now. And we go indefinitely in this direction, where indefinitely actually means that we stop at some number from 0 to 9 I have just written here an integer denoted in the decimal notation, meaning it's just the number, an integer number with which you are familiar from school. I have just denoted it with some uh, a0 to an, where each ai from a0 to an is just a number from 0 to 9, just your familiar number denoted in the substitute notation. Okay, and here you go indeed infinitely far. Or you can go infinitely far, maybe from some point we just have same thing, for example series, but you go into infinitely far and you have the same. So floating point numbers, that you should keep in mind, maybe to have some intuition, but you will not necessarily see a direct connection. Well, most likely you will not see this direct connection until some time, but we'll come back to it, and just keep in mind that what we are defining, you're actually familiar with it, even if you won't be able to make a connection. It requires time to actually see that this is okay. Let's jump into the abstract definition. So we have the set K with the first property of the set. There are two operations, and that is just some maps. Operations are nothing else but maps. And such operations that go from K cross K and go to the same set at whose cross product they start, at whose Cartesian product with itself they start, cross product because of the cross. Yeah, they are called closed operations, but no, we don't mention that because we just already have specified that this is just such maps, right? All right. And those maps do what? Well, they just take some pair of elements in K and they map that to some, actually, we denote it like that, right? This is actually a map that takes a pair of elements in K and maps that pair to an element in K. But we denote this element like this, just like same thing, only denote it in a way that we have less to write and in that it is more convenient to write, right? And for now, it's just maps. It could be for now any such maps that go from there to there, right? So it's not really a definition of how those maps act. It's more like just introduction of notation. Those maps are now only required to have this domain and to have this target set, right? All right. But now we begin to require properties of these maps. Well, there are two maps. Let's make a proper sentence out of it. And enjoying the following properties. Okay. Well, as customary done, we'll just call this maps addition and multiplication without thinking that we are now defining them in some abstract way. It will turn out that it is actually what we understand as addition and multiplication, but it will take time to really establish it. Okay, enjoying the following properties. Properties of addition. Okay. Well, except for this map being defined here, it has some structural properties. What others? Well, associativity. So with that, you're certainly familiar from the real numbers you know from school. And of course, as always, we adopt the convention that what is in the brackets is supposed to be the operation done first when we write such a mathematical expression, right? Because if we would write it like this, then first, if we don't know anything about this operation, then it would be ambiguous. We could think this is not a defined thing. When we only have this operation, then this operation acts on two elements. But what is this? What is acting on what? That could be interpreted as application of plus to AB, and then application of plus to the result into C, or it could be interpreted just as well as application of plus to A and the result of B and C after application of plus. So that is why we introduce those brackets to indicate that we actually mean this. First, we take this application of plus. All right, all right. And associativity just tells us we really require for this operation that it doesn't matter. And from now on, it will mean when this operation is the only operation contained in an expression, then live, we can just get rid of all the brackets, right? So addition is associative. So that property, we only state that property, but actually this property is extendable to any um, proper bracketing in an expression that contains only pluses. So in such expressions, uh, we can always eliminate the brackets. Okay, that is associativity. We have commutativity. With that, you should be also familiar from the real numbers. You know them from school. Commutativity. All A, B, and K. We have, okay, I have written it now like that, but let's write it in more customary notation. A plus B is just same as B plus A. So the usual properties that kind of make life easier in sense of uh, having to write down less. Right, and 3. Okay, what do we have here? There is a neutral element, and we call this neutral element. It's just choice of name, but choice of this name is very self-suggestive. Called 0 and denoted like that, like our familiar 0. That is element in K with the following property for all A and K, A plus 0, which is of course same because we know it of commutativity, but let's write it down. The same as 0 plus A is equal to A. And maybe notice here something. We are talking about for all, but of course for all means arbitrary. Actually, you should be already familiar with that after watching the basics of university videos. I think I didn't mention it directly, but it is obvious, like arbitrary in sense of having chosen anyone simultaneously. Right? Think about that maybe. What it really means. For all choices, it really works no matter what choice, but this choice is not specific, but really applies to all. So the choice could be anything and it would still hold. Okay, there is an inverse element to each element A, element K, that is, and is important, inverse with respect to addition, but now we list properties for addition, so that is clear for all A, element K. So we fix one, right? Fix one, but we could choose as with fix anyone, and so we could go through all of them separately, right? Any element K exists English element A minus 1 element K such that uh yeah, I'm using the notation from another setting. Of course, here just minus 8. So, and you can guess already what its property has to be A plus minus A is equal 0, and because we have commutativity, we have that. Okay, now properties of multiplication. So first check in your mind that it is our familiar properties actually. We just define it now in new for very abstract object. And I should probably mention why that has to be. You see, in mathematics, you have to establish everything. You can't say a word without having introduced it either as definition or procured it from some other already established objects or relationships, like theorems establish relationships, and you can make them imply existence of some things. But you actually can't talk about anything if you have not introduced that. That is why we have to really introduce real numbers, even though we could say, oh, that's those numbers from school. There are multiple reasons for that. I'll just state some. I think there might be a lecture solely about that, so I will just sketch some thinking that explains some aspects of it. First thing, we want to know in exact mathematical language with what we are dealing. We want to know what we are allowed to do and what we are not allowed to do. This very much distinguishes the university maths from the school maths, where what we are allowed and not allowed to do was largely implicit and just followed some kind of common sense. In mathematics, such a stage comes, but it comes much later. In the beginning, you have to define everything very clearly. That is, you have a lecturer, not necessarily, but your missions done by the lecturer are supposed to be filled by you. Yeah, it's just because of the time limits. But I think I will try to make a very gapless lecture. Okay, well, that's one thing. We want to know exactly what we are allowed and what we are not allowed to do. Another thing, having such an object in front of you, we have not yet defined it, but after we have defined it, is a very good exercise in getting used to mathematical thinking, in getting used to this kind of thinking where, yeah, there are many aspects to this kind of thinking which exhibits features of mathematical thinking. Let me formulate it in a general. Right. So there are multiple good reasons to start with that. And finally, for a mathematician, it is just an inner feeling that you are only allowed to get somewhere when you have established your footing from a point where your footing was kind of rooted in a non-questionable system. Such a non-questionable system I gave you in videos on basics of university maths. And you saw it was really solid. We just started by mathematical statements and only assumed two things, but I won't go into that here. So those three reasons. It gives good feeling to a mathematician. It encourages you to engage in mathematical thinking and actually it forces your consciousness and subconsciousness to just get used to everything like that. And we have to know exactly what the objects we are dealing with entail and what we are allowed to do with them. And exactly means exactly. Every step that is done in the beginning has to be based on what has been already established. It can't be in any different way. And of course, I will leave some things as exercises and will maybe regard some things as trivial enough. That is just the customary practice because of certain limits, as I mentioned, temporal limits, for example, that the lecture is subjected to. But generally, yeah, you have to think of this need to establish everything based solely on what has been already established, either in the lecture or by yourself. But in every step, this step should be should have been established based on what has been established, based on what has been established, back to the very basic definitions. All right. Now after this intermezzo, we look at the properties of multiplication. So I hope I could justify a little bit why we start that abstractly. And yeah, if you haven't already noticed, that's not calculus one for um, for let's say general STEM studies. It's calculus one for mathematicians, if anything. Okay. Okay. I should mention another thing if I haven't already. I forgotten. Typical mathematical illness. Okay. Um, I should mention that um, this course is not really a set of lectures which I thought through. It's rather that I will try to do the lectures spontaneously. That is, I will try to derive everything without preparation. So I'm actually doing it for myself. If you're just enjoying this format for some reason, or you think you can learn from it good nonetheless, then you can engage in following this course. Maybe just interesting to see how someone is struggling with simple proofs. Could also be joy in that, or maybe recap yourself, like I'm doing the proof and you are doing the proof parallelly. If you are already familiar with stuff, for example, in second term or something, so it could be enjoyable. I can think of multiple ways how to enjoy it, but yeah, it is something very special and you should be aware of it that it is not really a set of lectures. Okay, well, properties of multiplication, associativity, And okay, I'm tempted not to write that here, just copy from just write copy from addition, but okay, I'll do that nonetheless. But I'll do it quickly and without remarks because that really just copies what is written by addition for this other operation called multiplication. All right, commutativity, same. For AB, element K, we just have that AB is equal BA. Okay, so for multiplication, we also have some equivalent ways to write things, and that saves us times of writing. Okay, there is also neutral element and one element K with respect to multiplication, and we call it 1, very self-suggestive again, and of course we just have 1 multiplied by A is equal A multiplied by 1, and that is just equal A. And finally, there is an inverse element. Which element? There is an inverse element with respect to multiplication, or rather I should say to all mistakes, for all A and K without 0. And yeah, that is important. We cannot invert 0. Actually, don't know if we have to state is an action, but let's state it just like this because there are multiple ways to give the basic definition that are largely not that far from each other. Of course, they are all equivalent, but I don't mean that. I mean work involved to justify the equivalence. Row A element K without 0 have here exists a element K A minus 1. So we denote it as A minus 1 or 1 divided by A, but we usually denote it by A minus 1. And yeah, actually 1 divided by A is for now unknown. We cannot divide in that fashion yet, but okay, we will be able to pretty soon. But yeah, we have not introduced this notation yet, and so I should mention it. Okay, I mean this horizontal line for a fraction. Okay, so there exists a to the power minus 1. Okay, and this is just notation again. But of course, what does it do? Well, what could it do? Commutativity, and that has to be 1. Okay, and now we have this set of properties. You should already notice something. There are just two operations. We do not mention any subtraction or division, even though in your numbers you know very well there's subtraction and division, and those are valid operations, right? But we are introducing inverse elements. And the truth, the algebraic truth behind subtraction, at least from this point of view, we'll introduce video number 6 axiomatically, is that subtraction is simply application of addition to an element and an inverse element of another element. So it is not necessarily a plus minus a, but it could be b plus minus a because minus a is just a legitimate element of k for any a. All right. And same, of course, for division. Division is just multiplication with an inverse element. All right. Now, properties of 0 and 1. And you might be wondering why we even talk about that. Wouldn't it follow somehow? It's so natural. RHS of 0 and 1. 0 is unequal 1. But indeed, first of all, if 0 would be equal to 1, okay, actually, um, we could already derive it from there. But okay, I state it as an axiom. I can state a superfluous axiom. There's no problem with that. Superfluous axiom is an axiom that can be derived from other already derived or from other already defined stuff in definition or in an axiom. Right? So I don't need to include it in the definition if it follows from the uh, constituents of the definition. And I'm pretty sure that it follows now, because if we have those two operations defined and we define that there exists an inverse, but there's no inverse of z for 0, that actually follows. But since it is very important and is not just given because we know real numbers, not for that reason, but because we can show, and that is actually very easy. You can do it as an exercise that this follows. Can you do it as an exercise? Let me think. Uh, from this properties that already follows that 0 can't be equal 1. Yes, you can do it from that exercise, but at this point it would be a little bit different because you are not yet familiar with how to reason in this setting. But in a few minutes, you will be able to do that. All right. All right. This is already involved uh, definition, even though it is just the first part of the definition. But, well, okay. Uh, don't think, oh, what's that? There are so many words and symbols. You should be familiar with those words and symbols, of course. But, like, nonetheless, it can be a little bit overwhelming that there's so much. But think about it in the way of what is actually written there. Is there really something that involves a lot if we think about it simply logically? And you will notice, well, it's actually manageable. So even though there might be such inner psychological pressure, oh, there's written a lot, it might be complicated just because there's written a lot, you don't need to stress over it. Just go step by step in your mind and establish for you that everything that we have written makes sense. Make for yourself examples and things like that. I'm not making particular examples because that's at this stage you should just work out for yourself how you familiarize yourself with the definition. Uh, to me, it's, yeah, I don't know what examples I should give exactly. Right, I don't know where your prominence will be because it's probably also individual. So yeah, I'm not doing that yet. Okay, well, what do we do next? We have established operations and matrices. Operations and matrices. We have defined operations and real numbers. All right. Next, wait, yeah, not yet true. I'm always forgetting this by field structures. But of course, we have to have distributivity law. You probably recall distributivity law from school. It is properties, joint properties, or our joint property of addition and multiplication. And that is just the following, that for all a, b, c, element k, we have that c multiplied by a plus b is equal to c multiplied by a plus c multiplied by b. And phi commutativity, but maybe let's state it another time because it's so important. Phi commutativity, they then of course automatically have distributivity laws. Okay, well, up to this point, we are very general, only that I have hidden from you that this actually defines the notion of a field. I have also hidden from you some stuff which is rather trivial. Let's state that just on the side are properties implied by the definition. It's just very basic properties, but they are important by the definition so far. You see, the definition is not complete, but those properties are already there, and that is, we can already do implications with them because the resulting object, after the definition will be complete, will certainly enjoy these properties. And you might be somehow not happy that I'm interrupting the definition to state these properties, but you see that it has its merits. You have to wrap your mind about the first properties in the definition, and then we can proceed with others because they will talk a little bit about different stuff. And so it is actually a good thing that I'm interrupting the definition. That is partly why I do that. Okay, properties implied by the definition. Let's call it theorems. So I don't know what it should be called in English. Theorem one, and let's just go through the stuff like the neutral elements of addition and multiplication are respectively unique. Let's give a little proof so that you see a little how the reasoning works in this framework. Let's do proof for 0. That is the uniqueness of the neutral element of the addition. And proof for 1 you can do then yourself if you will have the need for that. Right. I mean, if you want to see how it goes immediately from the proof for 0, because oh, it goes same way. And of course, I'm hiding something from you. We could have based those definitions on certain algebraic structures. That is, some certain structures whose operations have less properties, or maybe there is only one operation defined with certain properties. So I'm hiding something from you because I don't want to overload it. But you can watch, for example, my video on matrix operations if you are interested in that. And you can invoke from there what algebraic objects are actually entering here, or what properties of what algebraic objects. Okay, and as I mentioned, there's also a general object which we have just up to now defined. Up to now, the definition of the first part of the definition of the real numbers just says real numbers are a field. So this is a more general structure that just enjoys all these properties and is defined exactly like that. And in more simple setting of the structures, we could just simplify these proofs a little, but we are not doing that because we don't want to overload the lecture with abstract stuff. I think it is abstract enough if you are seeing it for the first time, even though it's in a way familiar. Okay, let's do proof for zero. First of all, we have to contemplate what does that mean that the thing is unique, because it is not that trivial. What it means in mathematics is that any other thing that we suppose in this setting that enjoys those properties is actually equal to the thing that we suppose to be the one thing, right? So we assume there would be something else other than zero enjoying the properties of zero. And then we show that this thing is already equal to zero. Of course, it is symmetric, and it is just that we called this thing zero. But the thing is, if there are two things enjoying the properties of zero, given all those other properties of things in that structure, if two things enjoy those same properties, then those things would be equal. And you can think why it is uniqueness. You can see it as something trivial, maybe, or you can perhaps have trouble to understand that it really captures the concept of uniqueness as far as it goes. Maybe you have to think about what mathematical object is to really understand that. I had also some contemplations about it, but I don't recall in what video series. So you have to look for it. I don't recall really in what mathematical series I talked about mathematical objects in general. The quality of mathematical objects. I think in basics of university maths, actually. Yeah. I think there. Yes, yes. So I hope you watch the series. Okay. But now we apply that in context of uniqueness. Okay, let's do proof for zero. So accordingly to what I said, suppose there is E element K having the property of neutrality. And the property of neutrality of addition, of course, is just the third property, right? Having the property of neutrality of addition. And here we could have gone two ways. One way would be to assume there is such one non-equal to zero, and we would lead it to contradiction. Another way that I'm going, there is just one, right? There is some such, and zero was already there, or we have already stated there is already there. But this one that we are supposing is there could be also zero. We don't know. But we would now show that it is in any case zero, that what we have chosen must have been already zero if that thing has the property of neutrality of addition. Okay. And this then shows uniqueness for zero. Right. Then have. Okay. Now notice something. The information that we have about E in K is not only that it has the property of neutrality of addition. That is one thing that is obvious. But being in K and K having those properties, we can apply or use all those properties of elements in K that are actually already stated. Right? Okay, that's a good thing. If we need it, we can use it. We need it. Okay, and properties involving K also apply of some other elements, in particular of this element, and so on. Okay, then what do we have? Well, we have E. Okay, to start by what we have makes sense, maybe. Maybe not, I don't know. I don't know if it makes sense for you. And this, we know that because 0 enjoys the property of neutrality for all elements, but that is now an element of K, right? We have just taken element of K and have thought, maybe it has the property of neutrality of addition. Then what could we say about this element? That what we'd like to say that has already to be equal 0, so that it was actually 0 what we have taken. Okay, neutrality of 0, right? Because 0 is neutral with respect to any element, in particular to with respect to E, which is element of K. Neutrality of 0. And now what we are using is neutrality of E, because what we have assumed is that E has this same property, but we have that 0 is element of K, and we have that now E has this same property. So in particular, if A is equal to 0, E has this property. What does it mean? That means that applied neutrality of E allows us to say that is actually 0. And so this property of E implies that it was already 0. Okay. Proof for 1. That is that 1 is also unique. Proof for 1 is homework. All right. So you see, this proof was proved by shift of perspective. Or I mean, the leading principle of it was shift of perspective. This was the central part of the proof. And we just had to see, this is same. This is same. And that was by shift of perspective. That was the thing first to which the unity of 0 was applied. And then shift of perspective. This now was suddenly the thing of which the neutrality was applied. And it was applied on 0, right? All right. Proof by shift of perspective. Good. Okay, then we have that first property, and you have already seen a little of this reasoning. Then inverse elements, that is of addition and of multiplication, are unique, which A and K for addition, because for addition every element has an inverse element, in particular 1, and for each B element K without 0, for multiplication. All right. I don't know what our problem is. Okay. I think we can already do. Um, I'm just contemplating if we should do this proof. Well, maybe do it. Proof just for you to get familiar with it a little bit. It's not that interesting proofs, but let's do for. Should we make there a distinction? We want to have uniqueness. That is for each A element K, for each B element K0, we just take a look at inverse elements. Well, let's do for addition, for example. Let's do for multiplication, just to have another thing. Let's do it for multiplication. We already know how to prove uniqueness, right? Let's, I don't know, GC. No, of course we have first to take just some element of let A be element of K. Okay, to not confuse you, of course I could take any variable because it's another context here. It is just for each, so for all, but okay, let's do it without creating additional confusion because of notation. B in element K without 0 and G, C having the inverse element property, the inverse property, inverse element is also short called inverse, having the inverse property for B. And have all right. Let me think. What do I have to show? We have that those is one, and that. Uh, okay. What am I doing? And the order is doesn't matter, but okay, write it now in the right order. E C. Okay. But now, can we do that? Yes, I think we pretty much can. Yeah, okay. That's just the property of inverse, right? Inverse D inverse to B uh, C inverse to B. Okay, we should only have that. And now, well, if we have an equal thing and we just multiply by an equal thing, the equality. Of course, the equality stays the same, right? And we have certainly an inverse, and well, let's just take one and multiply G multiplied by B multiplied by D. I'm just multiplying on both sides by D, right? And on what side doesn't matter because we have commutativity. And we have T B multiplied by C. And this gives 1 because again, that is an inverse. T inverse of B And here, same argumentation. And this gives G is equal to C, right? G is equal to C by neutrality of 1, because we are multiplying by 1 here, obtaining C. Here we are multiplying by 1, B, and so obtaining D. Neutrality of 1 with respect to BC. Right. And that was it. Okay. Uh, okay, proof for congestion is homework, of course. Okay, what else would you have? Well, free um, for a element k, we actually have a multiplied by 0 is equals 0. So this familiar property is now abstractly derivable from already stated properties in the definition. Right, and of course it's same as 0 multiplied by, right. So you can think about how to prove that. And let's see other properties. I'm thinking about something. Let's say other properties you just have to think of, and when the need arises to use them, or either prove them, or I will hint at them, and so it will go. Right. I mean, our properties that are derivable for it because there are multiples that we do not necessarily all state. You just will have to derive them when the need arises. We'll have to derive them. Right, and usually it's just short proofs, so here are no problems at all with that. Yeah. But you are already seeing the scope. If you are starting by video, you are starting this feature, or you are seeing this feature of mathematics. If we are starting by a very compressed definition, define all of the real numbers rigorously, then many little elementary properties will be just, it will be just assumed that the reader or the listener will be able to derive them, because I can't just derive those, I don't know, 100 properties that you might need in different contexts, right? And maybe I should have also stated another ones, but for now, yeah, let's put it at that. Also, associativity of multiplication I have used here, of course, but yeah, that's clear. I just left, I just omitted the brackets, right, which actually should have been there. All right, let's go to the second property of real numbers, the second big property. And the second big property is called the ordering relation. Why ordering? Well, you can figure in a second. And for now, I want to postpone the topic of how it is actually defined. It can be defined very uh, based just on sets. There's no problem with doing that. But I don't want to overload this lecture with abstract concepts, as I said, so we'll just define it in kind of, let's say, an intuitive way. The ordering relation, and the ordering relation is called, and yeah, we can do that. It's just that we can do that if we do it so to speak, rigorously. But the thing is, there is an abstract, a nice, beautiful abstract framework behind it. And I would not actually like to hide it, but for sake of not overloading this lecture with abstract definitions, I will hide that for now. But we'll certainly look at that eventually. The ordering relation for A, B, element K, we have one of the let me think, because I'm not satisfied with that. Let's define it like that. We have one of the following two properties of the pair AB. And this is just two properties. This really is two properties, and we just denote it like them. I do not imply by that any meaning like bigger or equal or smaller or anything. It will arise. That's the beauty. That will arise automatically. That this is what we actually mean by bigger or equal or whatever. And that those numbers that should be bigger than those are really the bigger ones, just like that. All the numbers actually satisfy those relations in exactly that way, like we know that from school, what number is bigger, what number is smaller. That will just rise. So now it is just a choice of two notations, and it is just a binary choice, meaning either one or another is satisfied. So not both, but either one or another. And there are such things. We denote of a pair is satisfied. So for each pair, either one or the other. Right. Let's formulate it more mathematically, meaning precision in everyday language. We have exactly one of the following two properties of the pair AB, namely those, is satisfied. So we call those properties like that. And this is two different signs for those properties. We could also call these properties like CD. Doesn't matter. Just two properties, and for each pair, either one or the other is satisfied. Okay. Okay. And another thing, uh, you are probably already recognizing that, uh, that this means exactly that. If AB, if and only if. This means if and only if. If and only if in sense of application from the statement, from the logic of statements, right? So you should be familiar with logic of statements, of course. If you are not, which course basics of university maths. If we be doesn't satisfy. Yeah. Yeah, okay. It's ordered pair, so you recall in ordered pair, the order is important, right? Doesn't satisfy this, But for now, it's just names of properties. But recall it is an ordered pair and not a set, right? And order is important. All right. If A, B doesn't satisfy this, then it satisfies. Okay, it actually already follows from that because if that is not satisfied, and we know it does satisfy one of them, it satisfies the other twice further, so we don't need that. Okay, I thought for some reason that we need that, but no, we don't, of course. Okay, well, we denote for a B satisfying and denote um, it does not. And this is just such a relation. It's defined exactly like that, and the only thing that we actually defined is binary properties up to now. All right. So now what we also would like to have for first additional definition. Additional definition. For okay. We have to connect it with equality in some way because for now it is completely disconnected. It is just two properties. Okay. How would I do that when I already introduce it like that? Oh, if I do not connect it to equality immediately, and I seem to have trouble because it is completely disconnected from equality, and so no equality can be involved here. Okay. Okay, good. Let's choose that. Mhm. Okay. I think it is no problem. Uh, for a B, that's another property. For a B, okay. Have and this is not a statement. This is organic relation with following properties. With okay. just the title. For A, B, and K, we have exact one of it. Properties is satisfied. Okay. And this is continuing definitions. That is the case if and only if B equal A. And that is the mathematical object B is equal A if and only if it turns out that equality is connected to this kind of relation. All right. If and only if B is equal A. Okay. Can I do that? I should check it if there are no contradictions arising from that way of defining it. No, I can check it differently. Huh. Uh, okay. Oh, no. There can be contradictions. It can only be incomplete. Okay. Because if there would be contradictions in that, even though it is all properties of real numbers, then real numbers would be contradictory. But we haven't found yet contradictions in real numbers. So yeah, knowing that it is real numbers, I can know very cheaply if there are no contradictions, at least in cases when I only invoke properties that are already known and stated for them. Right, okay. Okay, but we have not yet arrived at real numbers. We define it like that. Okay. Then another thing, an important thing. This is not definition of equality. The definition of equality is just definition of equality of mathematical objects. K is a set, it contains mathematical objects, and so the equality is the usual thing. It is just the property. But you could, like, if you are thinking of this relation as really given, then you could use it as definition of equality, meaning that, well, it is equivalent. So in some sense, you could use it as definition of equality for this object. Okay, after I confused you a little bit, let's continue. Okay, that is the ordering relation. And I think that this is all we need here for that part. Okay. Okay. Well, do we need to see that? I think no. Okay, let's do the other part for yeah, we need another thing. Um we need another thing, we need that. Uh for A, B, and K with um A, B satisfying this relation, but and this can happen, right? It is just two non-equal objects that satisfy this that relation and equal that relation could be just called some C. So it is not connected to equality. We have to connect it to equality. This that is not connected to equality in our usually for now the only connection to equality that we have stated is this one. And we require only this one connection. So that is not equal, that is just some relations. That is just a thing, or we can say for each pair if it satisfies this relation or if it satisfies another relation. It's nothing else. Just some abstract relation. Okay. Mm, denote, no, right. And that is just definition, connotation. So if we write that, meaning that right A smaller than B. Alright, so the usual thing, but we just define this notation. So equality is not directly encoded in this. This will fall out, but will fall out in all relevant applications, mainly in implicit ways. Okay, but okay, we'll actually already have that from it. Um, because we have defined smaller in that way, right? Then smaller or equality. I should write or, not union. Then smaller or equality. We claim that it is equivalent to this. How do we see that? Well, if it is smaller, well, let's start here. If it is small, right, for equivalence, we only have to show both applications, and we can assume truth, and that suffices to show implications when we assume truth. Okay, if it is true, then this is true, or this is true. Okay, or maybe both. Alright, but both we already can see that it can be. So first say A equal B. How do we know that then this? Because we have that definition. Okay, then A is smaller than B. Then by this definition, A is smaller or equal B. And we call it small or equal as usual, of course, but it is only small or equal up to from this instant after we have shown this equivalence, which we are doing right now. Okay, now A small or equal B. Well, use this, invoke this, and then OR is already done. And that's it. So small or equal is already small or equal, even though we have defined it in a weird way, but pay attention of how we constructed it. It just was that the definitions go in the way that it actually popped out. Right. All right, and you might find it a little bit arbitrary what we are doing here. Some funny stuff, like defining that in that way to just have it fall out. Like, why not do it like define it directly? Well, one thing you should try to define it directly, and then you will see, yeah, it's not as simple as it seems to be. Another thing is behind there. There is certain mathematical reasoning, which I'm hiding, as I said, because this is actually a very general thing. Or this thing can be generalized. We can not only define on cases as properties, but very, very general. And those assumptions are kind of projection of this general thing on our setting, on this notation, and so on. Okay, another thing that we assume, I mean, uh, another property, and let's denote properties like, and then now, um, one of the four properties, okay. Okay, so to distinguish properties from notation, that is also property, that is a notation. And another thing, uh, for A, B, C, F, and F means here, of course, implication. So for all A, B, C, so what I mean is, of course, for all quantifier A, B, C, and K, when we have that, and what is that? Well, it's of course self-suggestive, but of course it means uh, and simultaneously we let's see have that A is smaller than C. It's called transitivity what of that relation. All right, and we have what's that? Well, that's called anti-symmetry. Anti-symmetry, why? Well, because it is only implying to that in that order, into that to that order, applying to that in that order, into that in that order, simultaneously, when if and only if it is equal. So in the symmetric relation, it would be just any pair if they are not equal, that would hold. So that's why anti-symmetry. The symmetry actually never holds unless they are equal. Right. Sensitivity and um, what else do we have? Mm, some kind of interaction with plus multiplied arithmetics, and by that we mean the properties of plus and multiplied that we that we defined. And that interaction is another property in the definition, and this goes as follows. When we have for C element K, so for instance C, have that A small equal B plus A plus C small or equal B plus C. Okay, for C smaller than 0, and we know what it means. Oh, let's do first the case bigger than 0, and not bigger or equal 0, but bigger than 0. By the way, bigger or equal we have yet to define, but it's kind of clear, right? But it is important that we do not consider the case of c equals 0, and, of course we don't. uh, okay, here I have already to explain what is bigger or equal. Define that as uh, um, okay, of course we could define it always, because or is actually like inclusive or, but just to have that already in our mind, let's show that it's really exclusive. Uh, show actually excludes possibility and that's simple. And we mean, of course, the statement, the logical statement, CA is bigger than CB, or CA is equal to CB, but written shortly, just this order between the operators. Okay, this because of what do we have? Let's call that EF, for example, and that is not, and that in particular implies, because you recall that that was equivalent to the okay, not necessarily, okay, that implies maybe they're all around, okay, but let's do it like that, and that is exactly that, and just the definition of this, right? And so we just have that that was equivalent to I guess equivalent okay, actually equivalent, right? That is equivalent to recall De Morgan, right? Which you also denote, of course, as it. And what we have now is just to show that this is not true, then only this can be true. Okay, in this setting, if we have EF and we have simultaneously, so we assume it is true and show that it leads to contradiction. And we have simultaneously this and this, which we have assumed where we started. Right? What does that entail? Well, it just means I think I'm doing funny things, but okay, it works, so I don't care. And that means what? That means okay, I know it actually means something. Okay, we have that is not equal. A, B, and K with what? A and equal B. Right, this. So what we have is that I certainly and U unequal F. So when we have those two simultaneously, actually already when we have that, but this does not imply this. Okay, let's continue. But what is actually that? That is that, right? That's actually an end, right? We have an end. We have an end here, right? Because equality of this to this, equality of this to this. This is by definition. This is actually also by definition. So let's look at the cases. Well, we have this end, and we want to show that this situation is actually impossible if we have the property statistics of, right? Because we want to exclude this when we start by this to actually have concluded this. Alright, why is that impossible? Well, now we have this end, and this end implies to either that and that would be already a possibility. I'm just using this distributive law, right? This is end, and this is or. And I'm just using distributivity law. And if we would put those together, then of course it will be a contradiction because a statement and its negation are true simultaneously. Right? You can look at the truth tables that this is never true, and this means a contradiction because we have arrived at something false. Right. All right. But now in our thing, uh, that could happen. In our thing, let us end with that. Right. Right, we have now to exclude that this is a possibility, but let's look at that. All right. Um, so that again, first we can put to it what we already know. But actually, we don't need to because that is of course impossible. I mean, always false. And that is just equivalent to false. And that is, I could write here a statement that is always false, but not doing that. All right. Actually, we didn't have that. We have that. No. That's right. That's right, because we use distributive law, right? And the distributive law works like that. Right. That is always false because no, that's actually not always false. Okay. Because that could be actually true. Of course. All right. I'm not seeing where we have. No, moment. Wait a minute. I have written that and because of war. Okay, because of war. And this is not okay, but this is okay. Okay. So we have that, all that, and we go F, E unequal F. How did I get that? Okay, I don't know what I have written here because clearly that has to be an end. I have that and that. Of course, it is clear from our tuition, but is it clear from our definitions? I claim this. Because here's a but, and but means, of course, simultaneity, right? So we have simultaneous that this is equivalent to this, but simultaneously is, okay, that was my mistake. Okay, so we have here actually and here we have in what we have then, the expression changes, and the expression is now, well, we have that, and we have that. And then it is 3 ends in a row, and 3 ends in a row just mean that it is a contradiction, because we would have that certainly this and simultaneously this is false, right? And there is another end, but it doesn't have any bearing on the situation. Alright, so but that was just a side calculation to establish But this leads to a contradiction. So then if we start by that, then certainly this okay, I was confused again. What? Oh, I didn't want this to be what? Um, I didn't want this to be what? It was this to be, I wanted this to be true. What did I want? I wanted to show that that excludes. Okay, so I want you to show that this is actually true. Okay, and then I will show that this is actually false. Okay, but why did I actually start to look at this? If I end up with this, then actually I would like to show that this is not the truth, but it is simultaneously, and it is obviously the truth. It is from our intuitive understanding. So something is weird. Okay. Now I'd like to show that it excludes inequality. Excludes inequality, right? So what I'd like to show is I have equality here. I have here a small equal. I have here more. I have here equality. Alright. And then we have that. Right, we have the notes. We have the notes with this end. Right. I would like to show that this follows, but this not. If I already have that, then this not is actually obvious if we go by. So no, this is true. Okay. Oh, yeah. I really. All right. So this is an end. This is an end. So this automatically implies that this is untrue because this is an end, and so those have to be true simultaneously. Right? So this implies untrue. Okay. That was funny thing. Okay, now I got it. I thought something's funny. Okay, so that really excludes that. So that's really an or between those both. Just like we established that it is an or between those both, but this was established by definition, right? That this was defined in a way that it makes this dichotomy, right? Here, right? But right. So, and we have that, and we have to rotate this. All right. Actually, is c bigger than 0? We don't have to. Oh no, I'm kind of I'm messing it up for you. Okay, here we have CA bigger or equal CB. But yeah, it's probably, I don't know, the reference actually it happens. Yes, I would say to me, to myself, that it is normal. Okay, well, the main thing is we have got it right in it. Alright, then we have that. Interaction with plus multiplied arithmetics gives us that. Now, have transitivity, have n symmetry. do we have to do something else? Well. Um, by the way, there is a nice consequence of that. Do we need that? No, we don't need that. There is a nice consequence of that definition here. That actually implies that equality implies that, and this implication is called reflexivity. This implication here, that equality implies that. This is called reflexivity. Reflexivity of this relation, of course, of this relation. And that you could just define as negation of this relation holding. So I didn't have to define it, but defining a dichotomy that exactly one of the following, of course, it means that it is negation because it's because of this exactly, which we have discussed. All right. Wow, this is the second part of definition. And before we dive into the third part and the final part, we'd like to look at some properties that it implies, at least some properties, that is a few. Let's call it theorem 2, properties of ordering relation. By the way, a nice fact. As you probably guessed, it is an ordering relation because we can order all real numbers nicely in this, right? If we take any two numbers, we just can order them, and this ordering is already given by such a number line, right? You can order them using this relation, right? All real numbers can order them properly, can compare them and then order them on the line, right? Actually, we need that now. Right, that's a 0. Right, now we'd like to prove some things. Oh, crap, what is... Right, now we'd like to prove some things. And, well, let's prove something that seems to be trivial. We'd like to just prove that 1 is actually bigger than 0. One smaller than 0, yeah, alright. So that thing that is just defined as neutral element of multiplication is nothing like a number like anything except bigger than the neutral element of addition just because of those properties. Let's try to prove that. I'm just trying to understand if we got everything, and I think so. I think everything that we had to really assume we got. So let's try to prove something that we really would like to have, right? That 1 is actually bigger than 0. Alright. Oh, how would we do that? Let's try the first thing that comes to mind when we have to prove some statement. assume one is more or equal to 0. And you see, I'm already starting kind of, or maybe it can't be seen directly, but I'm starting to think of those in the usual terms, because what we have defined is, except for certain for explicit relationships between numbers, is essentially all we know about those things, and there's not much more to be said. Explicit relations between numbers we of course have to derive, right? So try the most simple thing. Just assume that that is small or equal 0. What's the problem? Well, somehow we have to use the neutral property, right? Otherwise, it would be fine if we didn't have to use it at all. Okay, use the neutral property. Okay, that we can do. What can we do actually? Well, of course, it kind of seems that from those alone, since, well, what should we apply transitivity to? We only have two elements, and between them no relations are established. Then we have that. Okay, might be useful. And we have one of those properties. Well, this is what we used just now. Just assume the opposite. Alright, so we should somehow go with that, right? Looks like it. Okay. Assume 1 is more equal to 0. Then we just know from above, then 1 equals 0 or 1 smaller 0. Here we just used that thing. Right, right. But this is impossible with, okay. This is impossible by properties of real numbers, but we have not proved that. But you can prove that after we had those little calculations. You can prove that easily by properties of real numbers. Alright. Let me check it in my mind another time that it really works, that we can exclude that by properties of real numbers that we have stated. Okay. Okay, we also defined that it is impossible, but I also said that it is derivable. I'm not sure anymore if it is, because I have here thought of something, but I actually did a different thing. No, no, no. It's not derivable. because we have here just stated that for all what I had in mind, that that somehow states that for 0 it's not the case that there is an inverse element of multiplication, but no, it is not stated here. Here's just stated. It was my mistake in interpretation. Uh, here's of course just stated that for all those that are not 0, there is one, but here's nothing stated about 0. So yes, we have to state that. And so we can use that. Okay. It is not provable otherwise. Otherwise, really, otherwise, oh, wait a minute, why not? I'm just trying to understand why. Okay, okay, okay. Okay, okay, okay. Yes, we have to state it. We have to require it. Otherwise, we could have structure, which is maybe a peculiar one, but we could have a structure in which we have only one element, which is equal to 1 and equal to 0. I mean, it's rows, and this one element just satisfies everything. We have associativity for this one element, of course, because it's one element. We have commutativity, like we define that element to operations in any way that satisfy all of that. And there are really no contradictions with this neutral element with itself. And since there's only one element in total, only that element could come out, and yeah. And it's actually not difficult to check that any such structure in which we do not require that, and even a more simple structure, but in such structure with all those properties in which we do not require that, is necessarily that thing. It can't be anything else. So we have to require that to not generate to this thing, and this of course does not suffice. This was just a necessary thing to take 0 out, but this doesn't say anything about 0. Here it would say here would additionally be stated for 0 there's none, but this is not stated here. Right? It's just stated what is for those that are not 0, but what is about 0? We don't know. So yeah, by properties of real numbers, nothing goes. Impossible by properties of real numbers. So this case remains. So but then via neutrality of 1 with respect to multiplication, of course, and via the negativity of 1 by interaction have. Okay, neutrality of 1, right? Here just neutrality of 1. Here just this with iteration. We have assumed that it is negative, right? But for negative numbers, that works, right? And what does it mean that that works? Well, we are now interested in the case. Of course, I could say you can see by yourself, but let's do it. Uh, we have to show that same property applies to actually this, right? Here this property will soon apply to this, but this is just two cases. So property also applies. Uh, isn't it actually trivial? Ah, yeah, of course, not entirely, but yeah. Of course, since that is or, this is that is equivalent to or. Let me not write it like that. Um, since what I'm writing here, this here is equivalent to this being smaller, or both being equal, since that is equivalent, we have, of course, implications from or to from any one of them, because it would be or is satisfied, right? If it is one is true or satisfied, and we have implication, because this was equivalence of that to those two choices connected by the or here, right? Establish that. This is basically equivalence by definition of small, right? And we have that, and that means that C, C, B, no, we didn't have that yet. We have that. Which applies for negative C. Okay. And for that we had that that excluded equality, so indeed that is okay. We are writing or, even though one case can't occur, we are writing or. And in the case when I have not established that, just look at those definitions and establish that yourself. So if I have not properly established that, right? And now we just have that, and that excluded equality by definition, so that is excluded, and that remains C, C, right? Right. So those little things I won't do anymore because there's a lot of such little things and we want to get somewhere. Right. Alright, so typical lecture attitude. Okay, but well, why? And that is, we now have the that 1 is actually bigger than 0, and that is contradiction to the assumed 1 smaller than 0, contradiction to 1 smaller than 0, hence our assumption was wrong, and it can only be that 1 is bigger or equal 0, but 1 is equal to 0 is excluded. 0 as well as 0 it is generally excluded, so it is 1 bigger than 0. And we have proved that. Now, of course, I don't actually know what we should consider as next property of well, let's just list something like maybe it shouldn't even belong into order relation. Okay, so something that belongs to order relation. Uh, that was actually the main thing, I guess. Which number is how at which number is also same for new numbers, so seems not especially yeah. Actually, you might wonder, you might wonder why 0 is such a special number that we take exactly that to divide into classes of positive and negative numbers. Why exactly positive and negative? Why not take any other number a and just say, oh, here are like a positive numbers, here are a negative numbers. Why exactly 0? Because for 0, we were able to establish some other relationships, namely this one. This is the reason why 0 is the dividing point. Right, now let's think about, oh, I know. Of course, we don't have yet that. Oh, how could I even a equals 0? Then, of course, we have to establish that a bigger or equals 0. Of course, we have to establish that minus a is bigger or equal 0. That is like, and of course, we also have just you can establish this all and that little stuff that is involved. Of course, I won't do that. It's just too simple. Of course, abstract stuff, not that simple in sense of that you have to work here, you have to think here, but just too simple compared to what we actually want to do. Alright, and I think those would already automatically follow from this, but okay, doesn't harm to list them. We don't have that yet, so don't be fooled This is inverse with respect to integration. There's no such relationship at all yet. Uh, no such relationship at all yet. You should think about how this represented with some certain aspect of which one you could apply to imply that. Perhaps from these ones or from these ones, I won't tell. And this aspect, you should think about the structure a little bit about those properties, and you should see how you actually invoke that. Okay, okay. What else should we do? I think that is pretty much all. And other properties of such trivial kind we will just use, and I will hint at them. Okay, another thing we should certainly do is another theorem about properties. I don't know if we stated that already. Let's look. We stated that actually. Nice. We started that. Okay. Started that. Let's say maybe. Okay. Maybe. Then a equals 0 or b equals 0. Actually, not then, but having that theorem, you could replace it by if and only if, because you have to prove that. I should write it, of course. Proof. Homework. But okay, you can ask me about those proofs. If you won't be able to come up with that, then I will write you proofs. So you can ask me in the comments if you like. I will write you proofs that are missing. But you should do something yourself, otherwise it's for nothing. Okay, then a equals 0 or b equals 0, if we don't if, but I will improve this direction because the other direction automatically follows from that theorem. Proof that, and that's very simple. Okay, that actually actively involves theorem that you have to prove. And then either if equals 0, we are done. And that is equality. A is equal 0 or A is not equal to 0. Then A is multiplicatively invertible and a minus 1 and b equal a minus 1 0, and that is equal to 0 is no. As you know from this proof you have to do that is b, and that implies b equals 0. This no matter what case, because we know mathematical statement is either true or false, that is the whole mathematical world disparates into halves. The whole mathematical world really. Here is a equals 0, here is a n equals 0, and 1 has to be. Right. Okay. And in both cases of mathematical world, that is in the whole mathematical world, sum of those is 0, and with that, this is proven. Okay, what else do we need? Oh, well, I think at this point, we'll just establish our things as we are going. Our simple stuff, or I will hint at it and say that it is homework. We'll see. Okay, but you recall, and again, I have made that intermezzo so that you kind of get familiar with that stuff, at least a little bit. Of course, it is a lot. It is really a lot. And first lecture is always, first lecture in the semester at university is also always, um, for many students, I won't say for most, probably I should, but I won't, because I should not make such claims. We are doing justice, but for many, I can say pretty confident. So for many students, it's a horror, and that's normal. And what you're experiencing in the CEO is just this stuff, if you are experiencing that. Okay, now third property of the definition of real numbers, and the definition is finished. And to keep track of the definition, of course, you should not rely on oh, I have seen one time it works. You should have made notes and you should read them and you should recap it. You should recap the whole definition with all properties and things like that clearly, right? There were three big blocks of the definition, and now finally the third and final block is coming. Alright, that's great. After that, we can really engage with real numbers and do some amazing stuff. Okay, and the third is perhaps the weirdest. The third is called, it is also explicitly called axiom, and it is a supremum axiom. That is axiom about the existence of a supremum. Without that, we wouldn't have real numbers, but with that, and of course, taking all those that we already have about this object K, we have uniquely determined via this very abstract definition exactly our familiar real numbers, which we will have eventually proved even establishing that floating point shape starting very, very abstractly as you have seen. And that's striking, right? That's very impressive. But okay, we are not yet here. Supremum axiom. And the supremum axiom is kind of the thing that assures or ensures that we have no holes on real line. We don't have, well, actually, we have line already because we have the totally ordered real numbers, meaning that we have can compare and equal them, and then we can order them theoretically. And this axiom is what ensures no holes. There are really no holes. It's really very smooth, and it is as smooth as it gets. It doesn't get smoother. It is really continuum. It's really continuous object. All right. What is this axiom? Well, it is a little bit involved. Those axioms above, well, maybe they do a little bit in unfamiliar fashion, but there was nothing going on. But here already something will go on. For each bounded set M subset of R, definition bounded M subset phi is bounded if there is M uh, not same M of course. There is and let's call it S. No, let's call it B. No, let's call it U. Okay, if there is U elemental such that for all M element M have upper bound, what could it be? Just like that. But recall that this thing we have already established many properties of that, but you should think that is an abstract relation. Of course, you are allowed already to think that in terms of small or equal, because we basically established everything except for things that we have to establish yourself, but we assume them is established. So you can kind of start to think of that in usual terms, but never forget that it came from there, and occasionally you have to use that. Perhaps there's some balance because those familiar objects are defined now very rigorously, but you do not actually think you need to always think of those definitions. It's more like you have established them once, you have played with them in the beginning, you have acquired mathematical intuition, and you just go and can, when if you wish, anytime establish them, anytime establish all properties that result from them. So you do not actually actively establish all those properties that result. All right. All right. Uh, so this is definition of boundedness. There's just some number for which all elements in M are small or equal. And well, uh, examples think of something like, I don't know, set of some distinct numbers, right? And I could just take any bigger thing, or I could take the last number and could say that that is, we call it U. That is some U0. That U0 works. But that U1, let's call rebounds. Let's rebounds by such strokes. U1 works, U2 works, U3 works, and so on. But now we could have a continuous set, for example, set of all numbers from 0 to 1, and now 1 would work, and so on. But now we could have another set, some set on the real line that contains infinitely many intervals, right? So their length is diminishing, and their length is diminishing so that the sum of total lengths is 0, and but they all end here, right? And then that would be upper bound. So bounded sets are pretty normal thing. What is unbounded? Well, the whole real line. Unbounded. But not only, of course. You could just take this set of, uh, we don't know what it is, so in a way we know, uh, think of integers, but from the school, and for now just take for granted that we will establish them properly. We'll establish that integers actually work and things like that. Okay. This set will be of course unbounded. Okay, so any set at all, and we just say a set is bounded if there is such a thing which is really above it. Okay, and the axiom that is definition of boundaries says for every bounded set M subset of R, subset of R, there is S element R with S smaller or equal to B for any, and we mean by any here, of course, for each, for any upper bound B of M. S is called, now very self-suggestive, the least upper bound. Or supremum of this M. And we also define some stuff for set this unbounded, and that is just convention. We just say that set supremum equal infinity. Alright, alright. And of course, what the boundedness that we have here is from above, because we could have also go to the down end, and we could consider boundedness from below, right? And of course, there is another notion, but we don't need it yet. The superior axiom is just stated like that. Bounded from above. Okay, why did I say that we actually need this axiom for equals, and that axiom establishes exactly this? Well, just compare point 1, point 2, and point 1 to rational numbers, and you'll just see that those points are satisfied, and rational numbers are certainly not reals. So, and what is bad by rational numbers compared to reals? We have holes, as you know. Right. Few explains why we need supremum axiom to fill holes. Well, Q actually explains why we need something to fill holes. And indeed, the supremum axiom is not the only choice. We could have at least two other equivalent things, but we decide that supremum axiom is the thing for us, but we could have just stated another two equivalent choices instead, I mean, respectively each one of them, and that would also give exactly real numbers, and we could have derived the supreme axiom from them. But we don't do that. Okay. And bounded again from above, of course. Alrighty, that finishes the first lecture, and think about those concepts. Think why it makes sense. Think why we have defined it that way. Think what we did there. Think why we did those things. Try the exercises. Try the homework. Play with the concept. So really engage with it in your mind and in your technical occupation with the material. Really do that because otherwise um, it will be rather of little use. Okay. This finishes. So, what will we do in the second lecture? This lecture of Calculus 1. I'm not sure yet. I'm not sure yet. I think next up, establish number sets. I think we'll do that. But I'm not sure yet if we will really do that, or if we yet have to do other things. Actually, yeah, those others. Those are the only ones. So establish number sets and the end Q. And basically the only work that we will have to put in will be to establish n. To to uh, of course you could think, well, we could just sum once. And to some extent you are right. But we want to have the property of induction so that look at the basics of university maths videos. I think part 5. We have to have this property of induction already given as a theorem from our construction pen. And this is nice, right? So property of induction is suddenly not an axiom, it is a theorem. So n that arises in that way defined real numbers already has property of induction, must have. Okay, that's nice, right? Yeah, but it will be quite an interesting instruction. And I think, I'm not sure yet, but I think that we can already do that. Start establish number sets. And then we can already start. Then start with sequences and limits. I think we are then ready to start. So we start with the most basic notion of calculus, the sequences and limits. Yeah, I think so, pretty much. We do not have to establish anything else. Yeah, we have to establish those numbers, and we start with sequences and limits. And then we can share functions. And the number representation already. I'm not yet sure, but pretty sure. Closing point. But yeah, okay, I'm not sure because there are some issues that need to be addressed. But I think yes. Not yet sure, but pretty sure. And then we would actually essentially have our use, because we would have established a floating point representation. But I'm not sure if that would be exactly what, or, but I suppose yes. Okay, then I hope you enjoyed it. Well, let's wrap it up.